Okay, I just uploaded the project list. Three individuals suggested a project, so I've included that. I think you can, so I've indicated assignment to you. The rest, there are about total of 16, but about 13, I guess, from which you can pick. And typical project description would be something like this: a title, a brief description of what it is about, and then a reference that will get you started. And every project will have that. If you don't like any of the projects, and if you have something in mind you would like to still pursue, just let me know so that I can keep track. What I would like to do is, within a week or so, as soon as possible, I would like you to pick a project and start working on it. I hope to give only one more assignment on an important topic that I think is important for you to program and get a handle on. Other than that, all your time in the course should be devoted to making progress in the project. And I have suggested a timeline. So about 3 weeks from today, that is March 27th, I would like to get a progress report from you. Okay, and that progress report should have 10 pages maximum, double spaced. The fonts and everything is given there. A critical review of the literature in that particular problem that you have chosen. And that essentially means, from the paper I've given, if you go to Web of Science, you can search and very quickly, within 5 minutes, pick up probably hundreds of papers. But I would recommend that you pick papers that are most cited related to that area. You know how to use Web of Science, right? So use that citation sorting by the number of citations and pick the well-cited papers as, and if you have a review paper, pick that and include that in your critical review, just to relate what has been done in those 10 papers or so. Limit yourself to about 10 papers, 1 plus 9 others that you pick, that you will put in the bibliography. And then you start, it should include a critical literature review, the problem formulation. Of those 10 papers, you pick one that you're going to try to implement whatever they have solved, and a simpler version of it, that's fine. And if you have any questions, email me or drop by to engage in discussion so that we can define the problem, that you can do it in a reasonable amount of time. And formulate the problem, boundary conditions, geometries, etc. In those 10 pages. Okay, and then the next month, from May 28th onwards, you can start working before also if you want. But I would like you to focus the later part of the project period in implementing it in some software, whether it is COMSOL or Star CCM or your own software in the project that you have proposed. So that final report should be a maximum of 25 pages. That includes the 10 pages that you have done before, so additional 15 pages or so. And that should include, the 15 pages should include results and discussion. So it should include grid sensitivity tests, it should include any figures, tables, everything. So a total of 25 pages for the final project, including the critical literature review and model formulation. So upload that by May 1st by 4 p.m. and the oral exam will be scheduled 1 week from that day, May 8th. Okay, and that'll be a 30-minute exam for each individual. I'll put up a schedule on Moodle as we approach the date, and you just come into my office at the time, and by the time I would have your report and your project files, whatever COMSOL files.
So that'll be one-on-one?
It'll be a one-on-one.
So it's possible we can schedule it a little before?
Yes, you can. If you have to do it earlier, that's fine. Yeah. So that's the place where I kind of explore conceptually what you have picked up from the course by just listening to me. We haven't really put you to hard work yet, except for, I guess, a few assignments. And one assignment more that will be kind of hard, I think. But other than that, it's project. Yeah.
I think the qualified exam would be held on May the 8th and May 9th.
That early? No.
Yes,
No,
it's
no,
all
no.
Before graduation, yeah, a week before graduation.
8th and 9th?
Yes, because they need to have the results for non-thesis master students or that who graduate, so they.
Oh. Okay. Thank you. So what shall we do? You want to have it on May 2nd? Or you want to have it after the exam? I'm fine.
After the exam?
After the exam is fine with me. I just need to know what is the latest date by which I have to submit the grades. I can have it one day before that. I don't mind. It's a small class. I can figure out.
So May 3rd is Friday, right? May 4th is Friday.
Probably, I don't know. um, May 4th is Thursday,
May 5th is Friday.
5th is Friday. So you're saying 8th and 9th are the qualifying exam?
Yeah.
Okay.
I prefer 5 or the weekend.
But I'm flexible enough to have it on a day that you pick. In each individual, if you want to come and say, I would like to have it on this day, I'm fine. It has to be at least a day before the final grades are due. Okay? That's the only constraint that I have. I don't know when the grades are due. Hmm?
Just 12th is
10?
graduation. So,
Oh, 12th is the graduation. So everything is finishing this year early. Okay.
yeah, this semester it's
12th. Okay. So 10.
For graduating.
See, that means I have to have it on the 8th. So the choice is you can have it well before your qualifying exam. But it has to be after May 1st, I guess, after you submit the final report. I need to have the final report. Okay. I'm going to leave that open right now. So each one can email me your preferred time. And as long as two people don't ask for the same time, I will grant you whatever time. First come, first serve, right? So is that fair?
For the oral exams, more about the project or more about?
It's about your understanding of this course.
Okay.
So that would mean I can ask any questions about modeling, any questions about numerical methods, which is what we're going to start today, any questions about the assignments that you have done,
But
projects.
the topics you have taught,
Hmm?
like you can go very deep, right? Like you have taught about divergence curves, so
Yeah,
what
yeah.
extent are we, because that's something from your angle, but like what extent do we need to go?
Okay, my goal for this course is to expose you to the art of possible in modeling. Okay, and this is an elective graduate level course, so I'm not trying to drill something into you, right? I'm trying to enable some level of thinking in your mind, understanding, so that in future, wherever you are, oh, I've seen this, I can do this, right? That kind of a trigger, but then you have to go and dig deeper to get the job done. And that I will test in the project. How deep can you go into the project problem solving? Other than that, it will mostly be conceptual.
It's
Okay.
much like we have seen that, so we need to be familiar with what.
You need to be able to talk intelligently about turbulence modeling, about time averaging, about volume averaging, about things that I'm not going to say derive this equation or prove that, okay? But what do you know about these things? What kind of limitations do they place? What kind of challenges do they place? So questions on that level would be one part. The other part would be going into your project that can be as deep as we can make it. Again, one experience that I should share when I was a graduate student, and I've shared it with my brothers who are also did their PhD. After your oral exam, any oral exam, you come out feeling that you did terrible.
Yeah.
Okay? Always, the experience is always like that. Why?
Like interviews.
Hmm?
Interviews are like
So you're saying this the week before my defense?
When is your defense?
Monday?
Monday. Did you?
I'm actually working
You're working on that. Okay. So any oral exam, if it is done well, you should feel that way. The reason is it's a flexible environment, right? So I can ask you a question, and if you answered it perfectly, I can escalate it to the next level to see how far you know. Until you break down, until you say, I don't know this, then you feel terrible because you didn't answer the question, right? But I feel very good that you have answered that far, right? And that's what is important in passing such
So
exams.
like GRE,
Um,
first round easy and the higher.
yeah, like that. But in an oral environment, the flexibility is even more. And you can always ask questions that even I don't know the answer to. I just want to see whether you have the right idea to go in the right direction. So oral exams expect to feel miserable after you've finished it, but I'm not so terrible a person, so I won't push you all the way, don't worry. But the point is that there is so much to learn, and you cannot learn all of them in one course. It's essentially to expose you to fairly significantly deep concepts. We have talked about a number of things like stability issues and bifurcations and multiplicities and averaging, various levels of model building, right? So these are all important and useful in any area of engineering or science. Okay, the tools that you're going to see are also like that. Again, a lot of things, numerics, you will see, initially you will start with very simple thing. We have already seen it in a linear algebra course, but that is the basis on which all numerical analysis and numerical methods are built. So we should at least have a review very quickly today, hopefully, and then move on to nonlinear systems, and then we will see some very relatively recent algorithms for solving fairly complicated problems, phenomena. Okay, any questions on the projects? So if you don't like any of them, if you have your own idea, please bring it to me, but quickly so that you can get started. Don't forget about these two deadlines, March 27th and May 1st. Yeah. Oh, are you okay? Okay. Do you need some help? Somebody?
She just went down.
Oh, she fell down? Oh. Can somebody maybe take her to... Do you need to phone? Emergency?
There's a monitor you will call. Can you go there or you have to call?
Call emergency. Wait, can somebody talk to the front office?
Those projects, so we can just choose what we want to do. We don't need to consider other things. I think she might
No, just lay down. Don't try to get down.
she still had this paper before.
I think Jillian has a task with this company. You should get some water.
She can lay down on the flat area because of the temperature or something.
Yeah. Budget. Yeah, I'm parked in the stadium.
Yeah,
The
if
gates,
you do that.
the gates are not open.
But I could just tell them.
Yeah.
Yeah, yeah, yeah.
Yeah, I'll
Okay. All right, I guess there's one person who had a question about it, but I can the projects. But all right, so we are going to start the second phase of the course today, which is how do these simulators solve the problems? We have learned how the problems are formulated from concept into mathematical equations. These are often complex partial differential equations, nonlinear, and computers are very good in understanding, manipulating numbers and logic, but know nothing about differential equations or calculus, even though that's not true. The symbolic packages are getting more powerful. But still, most of the simulation engines are driven by numerics. And so we need to build up how these numerics are coded. And the beauty with these computers is that once you figure out and encode a particular problem, it's available for you to reuse forever. And so we can build on that. And so the simulators are becoming more and more powerful. And 10 years from now, the COMSOL that you're using today would become much more intelligent, driven by maybe artificial intelligence, in the way that you will formulate the problems would be different from mouse clicks and opening things from a terminal. But if you compare COMSOL 10 years ago and now, you will see phenomenal improvement in the mathematical modeling capabilities. So they have been putting a lot of effort, this is true of all simulators, effort in making the whole range of models available. And COMSOL is probably one of the most advanced in that respect, because it sees itself as essentially a PDE solver, PDE toolbox. And engineering and natural sciences are full of partial differential equations, whether it is electromagnetics, solid mechanics, fluid mechanics, it's all PDEs. And so they know, they've figured out how to solve these PDEs. And we are going to march towards understanding how these simulators handle the problem. So as I said, PDEs you cannot really solve, so you need to reduce them to ODEs, reduce them to algebraic equations, and solve the algebraic equations. This was done in the 60s. The first computers, really powerful computers, were built in the 40s and 50s. And by the 60s, we had reasonably good, powerful mainframes. So one of the first packages that came out was called LinPack. And LinPack is still available today for you to download. It's linear algebra package. So it solves all kinds of linear algebra problems, from Gaussian elimination, eigenvalue problems, etc. So today's lecture is going to be a kind of a quick overview of what goes into that, what kind of ideas, what kind of algorithms that go into that. You need to really spend a lot of time if you need to understand the algorithms to the level of being able to implement it. But that is not required these days. You need to have a conceptual understanding of what an overdetermined system is, what is rank, what is determinant, etc. And you can just call these routines in MATLAB. MATLAB is built on LinPack also, or any other package. Yeah.
So is LinPack and LabPack the same thing, or
LabPack is the later version of LinPack, right? And there is something called IcePack, which is for eigenvalue problems. And there is something called ScalaPack, which is a parallel version of the LinPack. And there is a package called PETC, which is, again, a parallel large system of algebraic equations using iterative methods. So we will review what is a direct method, what is an iterative method, what are the advantages and disadvantages. And you have already used some of them in your first assignment. conjugate gradient method, for example, CGS, is an iterative method. What are the ideas that go into that? And how do these ideas build up in analyzing, for example, stability, orthogonality of vectors, Gram-Schmidt orthogonalization procedure? Do these things ring a bell? Have you seen these before? What a Gram-Schmidt procedure is? No? Okay. So this is where I don't know which one you have seen, which one you have not. If I go through fast on a thing that you haven't seen, slow me down until at least you understand conceptually what we are talking about. Okay. So I guess I don't need to go through the representation of a matrix. Matrix is a collection of numbers, two-dimensional arrays, but you can generalize it to 3-dimension, 4-dimension, etc. In one direction, you call them tensors. In the other direction, you just call them higher dimensional matrices. And MATLAB actually has multi-dimensional matrices. Essentially, that means we have more than 2 indices. Okay? So if you have 2 indices, it's a flat 2-dimensional matrix. And a 1-dimensional version of it is essentially a vector. And you have the Gibbs notation, which is with an index. Or, the Gibbs notation is the bold one. So when indicated in a bold symbol, it means it's a vector or a matrix. And its representation in terms of components is indicated simply by putting a subscript, A as the same as Aij, for example. And MATLAB implements this beautifully. So in that sense, it's a beautiful language to learn linear algebra in an easy manner without worrying about programming constructs and programming structures. So once we define these entities, we define certain rules of operation between them. These are all generalizations. A matrix is a generalization of a number from a single scalar number to a vector to a matrix. And similarly, addition. You can take 2 matrices and add them. In MATLAB, you can actually enter something like this after you have defined B and C. But what does it really mean? What is the algorithm? What is the rule underlying that? It essentially says add every element of B to corresponding element in C and store it in A. So it's an element by element addition. Take an element from B, take a corresponding element from B, C, and add them up. So that requires immediately that the 2 matrices be dimensionally compatible. Okay? And if they are not, MATLAB should spit out an error. Now, it is commutative, meaning whether you do A plus B or B plus A, you will get the same result. And it is associative in the sense whether you do A plus B and then C, or you do B plus C and then A, again, you should get the same result. These are the properties of the addition operation that we define. So a scalar multiplication is if you take a matrix and multiply it by K, every element in that A is multiplied. So the index notation actually gives you the algorithm. All you need to do is put 2 for loops around it. That's how the calculations will be done, right? And similarly, the subtraction is the inverse of addition, and in index notation, you have it corresponding definition. Now, multiplication. The generalization of multiplication to matrices is a bit tricky, and it is done. These are all definitions. We can define any number of additions, operations, multiplications, and we do that because we have certain use for it. Okay? And the use, of course, is in formulating linear algebraic systems and solving them. So if I have 2 matrices A and B, the product is defined as, in the index notation, take a row of A and a column of B and multiply corresponding elements and add them up. And that will go into the corresponding element in C. Okay? So this has to be done for all I and for all J. That means every row in A and every column in B. Okay? So that is the definition. Again, MATLAB does it beautifully without having to code this. These are all hard-coded to speed up the calculation. And in MATLAB, the symbol would be simply this, A star B, once you have defined. But there is a requirement, a constraint, and that constraint is the number of elements in a row must match the number of elements in a column. Otherwise, you cannot define that multiplication. And the other thing to notice is that even if B and C are, for example, square matrices, B times C is not the same as C times B. Okay, so they are not commutative in that sense. What did I have? BC is not equal to BC. Oh my God. CB. Okay, I'm going to skip all these examples. This is how you would do it in MATLAB, entering a matrix, A matrix B, and then A times B. etc. So there is another product called the Schur product or the Hadamard product. You indicate it by a symbol, a circle in between the two operands. So this is called the operator in general. An operator is a rule for combining two operands, A and B, in a particular way. And MATLAB has a way of implementing this. This is kind of similar to addition. We take corresponding elements from two matrices, add them, and put it away. So here you take the corresponding elements from two matrices and multiply them. So it's called element by element multiplication. And in MATLAB, the syntax would be A star dot, I guess, or dot star. I'm not sure which way it is. So that indicates that combination of dot star, I think it's dot star, okay, that implements this particular algorithm, element by element multiplication. Otherwise, A star B is a typical matrix multiplication. Okay, and there is something called a Kronecker product between two matrices. And what this is you take each element from A, like A11, and multiply it by the entire matrix B. And then do the same thing, A12 with B, and then expand the size of the matrix that way. And the identity matrix and inverse. So the identity matrix allows us to define the inverse. Like subtraction is the inverse of addition, so division is the inverse of multiplication, right? So, and in a scalar system, the inverse of a multiplication is 1 over. So the equivalent of 1 in the matrix world is I, the identity matrix, which has essentially ones on the diagonal, zeros everywhere. So if you have two matrices such that when you multiply them you get an I, that means one is the inverse of the other. That is, B is the inverse of A, or A is the inverse of B, so that when you multiply them, you get the identity matrix. So these, when you are presenting it like this in an abstract manner, you might wonder, why am I doing all this? Where am I going to use it, right? So the obvious place where we have seen before would be when you are given an equation like AX equal to B. And this equation we will solve millions and millions of times. And not small matrices, large matrices of the order of 100,000, million, billion these days. Because the size of this problem increases with the number of grid points that we have seen earlier. Okay? And how that connection comes through the discretization process, we will learn actually how to assemble these matrices for a given ordinary differential equation or a partial differential equation. But when you have a system like this, the solution is given simply symbolically as A inverse B. Okay? So in MATLAB, you have a function called INV. And if you pass a matrix, it gives you its inverse. And once you have the inverse, you know B, you multiply the two through vector matrix multiplication, you get the solution. Okay? What algorithm does it use? It uses an algorithm called Gaussian elimination that we will very quickly see. Okay? But the idea of an inverse at this stage is, if you have two matrices that when you multiply, it gives you I, one is the inverse of the other. Now, exponentiation of matrices. Okay, so if I have A square, what do I mean? It's simply A times A, true matrix multiplication. A cube means A times A times A, etc. So we have a general understanding of what an exponential function is. Same thing applies to sine, cosine, etc. The exponential of alpha, where alpha is a scalar number, is 1 plus alpha, alpha square over 2. That's an expansion. So it's an infinite series, and it's a particular series for which we give it a name. And that function actually has a lot of nice properties, in the sense, if you take its derivative, it is the same function. It's a beautiful property of the exponential function. So if you have an exponential of a matrix, what does that mean? What kind of a meaning can we give it? It's essentially the same expansion, but using matrix. So 1 plus A square over 2, but A square is this product. A cube is this product, etc. So it's essentially an infinite series. Now, if you ask MATLAB to find EXP of A, what does it do? And for that matter, if you ask it to find EXP of 2, what does it do? It just takes 2 and plugs it in here, takes enough terms in the series to give you results accurate to about 16 digit places. Because it's an infinite series, it has to truncate it. So that's a first introduction to truncation error. an error in a computation where you arbitrarily decide I'm going to keep only these many terms and leave everything else, and that introduces an error, and that error is called the truncation error in a series. And that truncation error, the number of terms that you need to keep depends on how many digits accuracy you want to keep, as well as the number that you are exploring. For example, if exponential of 0.1, I will need only a few terms, because every term, as it's squared, it becomes smaller and smaller very quickly. Okay? But if I have exponential of 2, 2 squared, 2 cubed, 2 to the power 4 become larger and larger. But is that series still convergent?
Yes,
Because of the factorial in the denominator. So it is convergent, but it converges slowly, which means you need to take more terms in that. So you can try writing your own exponential function to see how you would implement these ideas of taking enough terms, whether it is sine or cosine or exponential, whatever these complicated series functions, you have this idea of a truncation error that comes out. Now, transpose is another definition, which is essentially exchanging rows and columns in a matrix. And in index notation, it is simply this: Bij is Aj. And transpose of the sum of two matrices is essentially sum of the transposes. That operator can be taken inside. But the product, the transpose of a product of two matrices, AB prime is B prime A prime. And once again, you can put this in index notation and show that it is actually true. Or you can go to MATLAB and test it out in a few cases. There are lots of matrices with special structures. One of the most important structure is the lower and upper triangular matrix. It's extremely useful in solving large system of linear equations. It's called the LU decomposition of a given matrix. And it is important to understand this concept and relate it to the Gaussian elimination method. Now, a diagonal matrix is essentially one that has only diagonal elements. A lower triangular matrix is one that has non-zero elements only in the lower part, and similarly an upper triangular matrix is one that has only in the upper part. The lower part are all zero. It turns out that when you use a Gaussian elimination, you are actually reducing the matrix A in the problem AX equal to B into a form where you eliminate all the variables in all the other equations. So you're making it into an upper triangular matrix. Okay? And then the inverse process will give you a lower triangular matrix from which you can construct the solution. So we will see that process also. So then there is a most commonly encountered matrix structure is so-called tridiagonal matrix. So basically you have three elements. This occurs whenever you're doing discretization of differential equations. And it's a very effective method for there is an effective method for solving this called the Thomas algorithm that we will see as well. And a generalization of this one would be so-called block tridiagonal matrices, where you have a larger matrix that consists of three blocks. Okay, here there will be a block, and that block itself will be tridiagonal, and there will be one element, and there will be one element, and then here again tridiagonal, and there will be one element there, and everything else will be zero. So this is a 3x3 block tridiagonal matrix. It occurs in finite difference methods in 2 dimensions in partial differential equations, for example. Determinant. Do you remember what a determinant is? It's a scalar invariant of a matrix. It's an invariant property of a matrix, and it is defined in a kind of very weird abstract manner so that it becomes an invariant. Okay, that is, no matter how you calculate it, you will get the same number. And what is the definition? It is the summation of all possible products that you can form from a given matrix, taking only one element at a time from each row or each column. So conceptually, it's very easy to state, but computationally, if you need to develop an algorithm, it's very messy. And if you have to, this is a definition that I took from the book by Amundsen on linear algebra that came out in the 60s, and that essentially implements that notion: summation of all possible products So each one should have, if it is an n by n matrix, should have a product of n terms. But it should be such that no term can come from the same row or same column. Each one has to come from a different row and different column. So if you have picked one A11, row 1 and column 1 are out. The next number that you pick should come from second row or second column onwards, any one of them. So you pick in that combination. So you have to try for all combinations. So if you pick the first one, the next one, the chances are, available opportunities are n minus 1. The first one you can pick in n different ways. The next one you can pick in n minus 1 different ways. The next one you can pick in n minus 2 different ways, because each time you make a decision, the available chances reduce for you. So if you continue like that, you will find that there are n factorial terms. This summation is actually n factorial terms. Factorial n can be a very large number. So even if you have 100 by 100 matrix, 100 factorial is going to be a huge number to find all the products and add them up. So you will never implement this algorithm, even though it is an algorithm, meaning a rule that you can implement and write a program. You will never do that because it will be extremely inefficient. Because linear algebra is the core, at the bottommost part of this entire numerical methods of solving, you want to achieve efficiency as much as possible, because this is going to be used literally millions of times. Any algorithm that you develop in this plane has to be done in the most efficient way. LinPack, IcePack, ScalarPack, they've all been developed over a large period of time. Of course, there are still, as new architectures come in hardware, you will see improvements in these algorithms. But most of the basic ideas have been worked out to be in a very efficient manner. And one of the things is there are nice properties that come out of the way that we have defined. Okay? So if I have a diagonal matrix, what is the determinant of that? Simply product of all the diagonal elements. If any one of the diagonal elements is 0, what is the determinant of that? It is 0. Okay? And what is the determinant of a lower triangular matrix? It's also the product only of the diagonal elements, because for every element you pick on the other side, you have to pick one from the opposite side. So it's only full of zeros, right? So they will all cancel out except for the one on the diagonal element. So if you give me a matrix A, and I suppose I can split it into L and U, then I can find the determinant of L very easily, because just the diagonal elements, and the product of all the U's, and the product of these two is the determinant of the original problem. So one of the most efficient ways of finding the determinant of a matrix is essentially do the LU decomposition and find the
So
determinant.
for Gaussian elimination, like I thought L was a unique lower triangular matrix, so its determinant will always be 1. I mean the diagonal terms are all 1.
In what? In
Gaussian elimination, like when you break down L and U,
yeah.
L is the unique.
There are we will talk about it very quickly. You have when you have, if you are given a matrix A and you have to write it as a product of L and U, this is unknown and this is unknown. A is known. So you have n square elements in A. So that equation essentially says that there are n square equations, right? But you have how many unknowns here? N square. N square. So there are 2 n square unknowns, but only n square equations, right? So you have n square degrees of freedom. So you can exercise this degree of freedom to give any structure you want to these products. So we choose to say I'm going to make one as lower triangular, and I'm going to make the other one as upper triangular. When you do that, you will still find that there are n degrees of freedom left. And you can use that to say I'm going to make U diagonal 1, or I'm going to make the diagonal of L 1, or I'm going to make the diagonal of L the same as U, I don't care what it is. Just additional constraints that you can make them equal. Each one gives rise to different, slightly different variations in the names. One is called the Krauts, another one is called Doolittle, etc. Right? But the basic idea is that you have excess degrees of freedom that you can dispose of to give any structure to these decompositions. Okay, so if I have any row that is multiplied by k, that is equivalent to multiplying the determinant by k. The determinant just becomes a scalar multiple of the original matrix. There are a few other rules like that. One of them is if any row is 0, determinant is 0, because you'll always have to pick one element from that in all your products, and it's going to be 0. If any two rows are interchanged, the sign will change, and that result comes from the fact that in the definition of determinant we have this minus 1 to the power h. And h is a number that is determined in such a way, the second subscript that you see here, L1, L2, these are determined by which row and which column you pick the second number. You pick one according to A1, A2, A3, and then the second index you pick from the other non-used rows or columns, and they are going to be in different order. So you need to find out how many times you have to switch them to put them in the right order of 1 to n. So if it is even, it'll become minus 1. If it is odd, it'll become plus 1, etc. I'm really going very fast because it's essentially kind of trying to recall things that I think you would need as we move on, particularly when we are looking at things like Gram-Schmidt procedure. We need to know a little bit about these notions. So there is something called a Laplace expansion, which is slightly more better definition algorithm to find out the determinant, one that we have learned when you're doing things by hand. And what is that? If you give me a 3 by 3, A11, A12, A13, etc., you just take the first one and then take the second cross and multiply it. Similarly, take the next one, but put a minus 1 there, and then cross out that row and column, and whatever is submatrix that is left, you take the determinant of that. That's essentially what it says. You can do the expansion along any row or any column, but you take that row and strike that row and column, and what is left with is a submatrix. Okay? You find the determinant of that. So you have delegated this algorithm to a recursive one, where you need to keep calling to find the determinant of A. You need to find the n determinants of n by 1 matrix, submatrix. Each one can be called. If you write a routine, it can call itself recursively and assemble the determinants like that. Again, not a very efficient way, but very intuitive way, because we have learned, I guess, how determinants of small matrices are calculated using this idea. And I guess there is a 3 by 3 example there. Kramer's rule, you're all familiar with Kramer's rule, right? So let me just skip that. Matrix inverse. Okay, that's an important concept, because the essence of solving linear systems lies in our ability to invert a matrix. That's because X equals A inverse B. Okay, so we have seen the Laplace expansion of a matrix. Okay, but we understood what a concept of a matrix is. If AB is equal to I, then A is B inverse, or B is A inverse, whatever, right? And now we need a rule, an algorithm, to be able to actually compute the elements of B, or the elements of A, the inverse of a given matrix. And one of the algorithms can be developed by looking simply at the definition of a determinant and the Laplace expansion for the determinant. So if I take the original matrix and replace the column K in the original matrix by the right-hand side, okay, so if I have AX equal to B, I form a matrix, a new matrix. I call this as A of K, and that simply is the original matrix A, but with the column K being replaced by B. And then I do the expansion of the determinant around that column. So this is the Laplace expansion. So B1 times the submatrix A1K, B2 times the submatrix A2K, etc. Right? So by Kramer's rule, which I just skipped, and Kramer's rule is essentially saying that if you give me, for a 2 by 2 system, if I want to solve for x1, x1 is simply determinant of A1 divided by determinant of A. A1 is first column replaced by B. Okay, so if I extend that, so I can find each one of these components, x1 to all the way to xn, by simply using Kramer's rule. okay, which is the determinant of AK divided by determinant of A. Okay, and the determinant of AK, I have given you a template for that. You can replace it for each row. But now this looks like a vector matrix product, right? So I can assemble all this back into a matrix type form, whereas the left hand side becomes a vector and the determinant is just a scalar number. So I can take that out, and then what I have is a matrix A11, A21, AN1, which I arrange in this row, and then a vector B1, B2, Bn. So if I carry out this multiplication, I'm going to get the first row. If I carry out the next row with that column, I'm going to get the next equation. So do you follow what has happened? I've used Cramer's rule to construct the solution. So now I have an algorithm because this product is what A inverse is. Okay? And I know how to calculate the determinant. I know how to calculate each one of these determinant of the submatrices, A11, A21, etc. Again, not a very efficient way of doing it, but at least I have a way which would work for 3x3, 4x4 small systems. I can write a code. Okay, so that's capturing what we just wrote down earlier. So B, which is A inverse, and this matrix is called the adjoint of A. Essentially, take the minors of A and then transpose them, and that gives you the adjoint, and then divide by the determinant. Now, it turns out that the inverse of a diagonal matrix is very simple, just 1 over D11, 1 over D22, etc. You can verify that easily because when you do the D times D inverse, you will get I automatically. This is where things get interesting and powerful. Now we are seeing some of the most powerful methods for solving system algebraic equations. So the question is, what is the inverse of a triangular matrix? I'm going to go through this in some detail and then LU decomposition, etc. I have the notes. You can study it if you want, but we are not going to go through it in great detail. Okay. So the problem here is, if you give me a matrix, an upper triangular matrix U, and I want to find its inverse. So I call its inverse as V, which is U inverse. Okay, but I don't know the structure of V. Is it going to be full? Is it going to be upper triangular? It's going to be lower triangular? I don't know, right? But I know what I want it to be. So if I take U and multiply it by V, I should get the identity matrix. So I'm going to treat all these as unknowns, right? So there are n square unknowns in that. How is she doing? Is she okay?
We don't know.
They took her in?
Yeah.
Okay.
Our friend, yeah, so I'll take care of her.
Okay. 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 Thank you. Thank you all. Yeah. Okay. So we are really going very fast review of linear algebra. A lot of the things should be very familiar to you, but it's also being recorded in case you want to listen to it. But the purpose that I'm going through this very quickly is to get the playing field level and recollect some of the ideas that we would need as we expand this into some of the more powerful algorithms. What is orthogonality of vectors and eigenvectors, properties of eigenvectors, etc. So we're talking about the problem of inverting an upper triangular matrix. So you're given an upper triangular matrix U, every element there is known, and I need to find every element in a matrix V, which when multiplied by U will give me the identity matrix. Okay? So what is the structure of this going to be? Immediately I know that I have n square unknowns in this, and I have n square equation. Okay? So if I start formulating this problem, and this is the idea that I think that you should get. How does one come about developing these algorithms is to think about it in a way that you figure out what is the best way to sequence the calculations. For example, if I had done this, taken this row multiplied by this column and set that equal to 1, I will get one equation. And I can do that for first row with second column, first row with third column, so I can assemble my n square equations. And I can be bewildered and say, okay, how am I going to solve this? Okay, because what will happen? U11 times V11, U12 times V21, all these are unknowns. right? V11, V21, V31 are all unknowns. But look at what happens when I pick the correct row and the column to carry out the multiplication. For example, I take the last row and multiply it with the first column. What happens? 0 times that, 0 times the second one, they are all 0, right? So I have U11 times Vn1 equal to 0. But Unn is not equal to 0. If it is equal to 0, what happens? The determinant is 0, you cannot invert it, right? So it is not 0. So what can you conclude from that? Vn1 is 0, right? And you do this process going upwards like this. So that means you're going to find the next one here. That means you need to take the second last column with the first, second last row with the first column. Okay? If you sequence that, you'll find out that all the lower diagonal elements are 0. You just have to do it in a particular order, starting with this element and going up all the way, and then this one going up all the way, and you'll find that all of them are 0. And that is what this statement says, that Vij is equal to 0 when I is greater than j. Okay, so immediately we know through this logic that the V matrix is also going to be upper triangular. If U is upper triangular, V is going to be upper triangular. Our goal is to invert this matrix with the least number of multiplications and additions and subtractions. Okay, so if I know all of them to be 0, I don't even worry about calculating them. Okay, I just know that, and I don't even allocate space. These things become very important when you're doing very large system like 100,000 by 100,000 matrix. You don't want to waste storage saving elements that are 0. Okay, and then what you need to do is do all the diagonal elements. How do you do the diagonal elements? You just take, once you know that these are all 0, you take this with multiply by this. So U11 times V11 equal to 1. So V11 is 1 over U11. Okay, so using that logic, you basically found all the diagonal elements as just the inverse of the diagonal elements on the other side. Next, what you do is ith row of U with the jth column of V. Take the product, okay, and you will get an equation like this after dropping all the zeros. And you will find that in each one, you have only one unknown, Vij. Uii is known, and these will all be known if you do the calculation in a particular sequencing again, from the last to the upwards. Okay, so if you do that, you will be able to, with just each equation having only one unknown. You don't have multiple unknowns in the same equations. You're not once again solving a system of equations. Okay, so this turns out to have the least number of multiplications, which is one of the more expensive operations compared to addition and subtraction. So that algorithm can be coded. I think I might have a MATLAB code in a few lines. Okay, so you give me U and I return V, and this is the algorithm that I use. I don't even store the zeros that I know, right? So there is one loop that calculates all the diagonal elements, and then there are two nested loops, okay, to calculate all the upper elements, one column at a time, going from bottom to top, one column at a time. Okay. So you can see that I going from j minus 1 in decrement of 1 to 1. Okay, right above the diagonal element and going all the way up to 1. Okay, and do this for every column, j equals 2, 3, 4, n, and you found out all the elements of V. Any questions on that? The ideas involved in that are very important because it tells you that if you sequence the calculations in such a way that you can develop an extremely efficient algorithm, no matter what the size of the matrix is. Now, the same code will handle 100,000 or million upper triangular matrix of that size. Any questions? Gaussian elimination. I think you have seen that. Do you want me to go over it? I'll just give you this piece of logic and the code that follows it. And what I want you to observe in this one is the the Gaussian elimination basic idea is make the diagonal element into 1 by dividing every element in the first row by A11, and that is done in this box. So you need a loop. This is how I figure out how to develop the code. So I need a loop in MATLAB to calculate that first one. And then I want to make all the elements in here 0. I need to figure out what operation I need to do to make this 0. That is, take the second equation, multiply the first equation by A21, subtract one from the other, that cancels it out, cancels this out, so I don't really actually calculate that because efficiency is important. Right? I don't apply the operation of calculation that will make this 0. I just figure out what I need to do to make this 0, but apply it on all the other elements. Okay? So here k goes from I plus 1 to n plus 1, not 1 to n plus 1. Starts from the next one because I know already the previous one is 0. Okay? But this box has to be repeated for every row. So I have another loop. I figure out what that loop should be. J is equal to I plus 1 to n. That is from the next one all the way to down. Now the same thing is going to be used for the next column. Okay, and that loop is this one, for I going from 1 to n. So essentially a few loops, and the logic to figure out how to eliminate how to make the element 1, how to eliminate all of them. With this block, you converted A into an upper triangular matrix. The code, again, its MATLAB code is there, but I've given you here, but I've also put them together. So at the end of it, you will have a lower triangular matrix. Now, in this one, I have shown with an augmented matrix where the last column is the right-hand side vector B. So you're carrying out the operation on B as well. That's the problem with Gaussian elimination. Gaussian elimination, you need to know Ax equal to B beforehand. So that means you need to know both A and B, and you apply these operations. And then what you have is in the very last equation, you have only one unknown. That is xn, which is equal to this. And then you start the back substitution. Okay? And that essentially makes this matrix into an identity matrix. So it's a way of making a given matrix A into an identity matrix. So the operations have not been explicitly captured into a matrix called A inverse, but they have been implicitly used. So if you give me a different value of B, what do I do? I need to go through these operations all the time again because I haven't captured those operations, right? That's one of the problems with Gaussian elimination. And we have this problem of solving for the same A for different right-hand sides B repeatedly. And this is why it will be useful if we can find an algorithm that inverts this, captures it, and stores it, so that the problem is converted only into one vector matrix multiplication. Okay? And LU decomposition achieves that using the efficiency of Gaussian elimination, capturing it. So the A inverse from the adjoint and the determinant is an extremely inefficient way for large systems. But the LU decomposition is an extremely efficient system. Why is that? Because inverting a L or inverting a U, we already developed an algorithm. It's extremely efficient and easy method to do. Okay? Any questions on this? I'm kind of going through the important conceptual ideas in the algorithms. Okay? So this is the actual code for Gaussian elimination. As you notice, you need to give both A and B, the matrix A and the vector B. And you see it's a very simple piece of code. There are problems with this. What are the problems from your knowledge of Gaussian elimination? What are the problems that you can encounter when you're going through this elimination process? You are having terms like subtraction here, A22 minus A21 times A12, right? That could be 0, right? Or a very small number, close to 0. When that happens, what happens? You are going to divide somewhere by that number. And where does that happen?
In the next loop.
It comes in the next loop. In the here, AII, a diagonal element. If the diagonal element becomes extremely small, that number is going to blow up. Okay? So division by 0 doesn't necessarily mean that it's a singular matrix, because we are in the process of elimination, right? So we are in the process of elimination. So if we have done this elimination and we have retained the structure and the last one turns out to be close to 0, then what happens? Then it is a singular matrix, because then you have an upper triangular matrix and the determinant of it is the product of all these. But when you are somewhere in this stage, the diagonal becomes 0, it doesn't mean that the matrix is singular. It doesn't mean the determinant is 0, right? So what do?
Switch the.
You switch. This is called pivoting. Okay? So you can always switch two equations in the order. It doesn't change the problem. So you would then exchange that row with any row below that and switch it around, and then you can get over the problem. Now the code that I've given you doesn't have that. That requires a little bit more logic to be able to exchange and keep track of changes in the indices. And that is, so this is why I call this as a naive Gaussian elimination, because it doesn't use pivoting, and it could fail in those cases where you get accidentally a 0 on the diagonal, but the problem is still well posed. And that idea is illustrated in this 2x2 example. Okay? That is the errors introduced by lack of pivoting. Okay, why pivoting is so important. So consider two equations like this, but one is multiplied by a very small number epsilon, close to 0, small number. Okay, so what should the solution for this one look like? If I apply the naive Gaussian elimination, what will I get? If I apply a more thoughtful method, what will I get? Okay, well, what should the solution be? If epsilon is 0, first one tells you x2 equal to 1, right? If x2 equal to 1, x1 is equal to 1. So 1, 1 is the correct answer for this as epsilon approaches 0, right? But if I apply the Gaussian elimination without switching these rows, what I'm going to get is something like epsilon 1, 1, 1, and I apply the Gaussian elimination and eliminate x1, and I get an equation for x2, something like this. So I'm going to write x2 as 2 minus 1 over epsilon divided by 1 minus 1 over epsilon. What happens to that term as epsilon goes to 0? It doesn't blow up. Because this will blow up, this will blow up, which means it makes these numbers irrelevant, because these two numbers are very large. Imagine epsilon is 100,000. 1 over, epsilon is 0.00001, right? So 1 over that will be 100,000 here, 100,000 here. So this is very small. You can drop that out. So it's essentially 100,000 over 100,000. So it's 1, right? So x2 approaches 1 as epsilon approaches 0. Okay. Now, if you take x2 as equal to 1 and continue getting the solution for x1, you will get x1 as this. Okay. So what does that tell you? It could be anything, because you have 1 over epsilon minus 1 over epsilon. You would argue that it should be 0, but we know that's not the right answer, right? But if I actually run it in MATLAB using the Gauss program that I wrote, I get results anything like 1, 1, 2, 1, 0, 1. Okay? Why? Because it depends on the precision to which I calculate. So by controlling the value of epsilon to be 10 to the minus 15 or 16 or 17, I can get any of these results. Okay? The reason is, when I take 1 over a small number, I get a huge number. I'm taking the difference of two huge numbers. So this illustrates this notion of round-off error. We talked about truncation error as an important concept that we need to understand in numerical analysis. Round-off error is another important concept that we need to understand. Okay? So here, this is a very large number, and this is a very large number, and you're taking the difference of these two large numbers, and if they are larger than 16 digits, MATLAB carries about 16 significant digits, right? If they are larger than 16 digits, when you're taking the difference between them, they're going to get washed out. And that is what is called the round-off error. And direct methods, Gaussian elimination is a direct method. What is the direct method? It tells you that you can get a solution in a finite number of operations. Okay, there is a direct algorithm, and each value can be calculated directly without knowing anything about any other value. In an iterative method, you make a guess for the unknowns and then try to improve it successively. And so those methods actually have a natural ability to get rid of errors because the first guess you make has the largest error, and then the algorithm cleans it up, converges. Okay, but in here, any error that you introduce at any one of the steps is carried forward in every other calculation. Okay, so if you go back to this algorithm, the pictorial one, if I introduce an error in that calculation in the 15th decimal place, there is no mechanism to get rid of it. It will be used in subsequent calculations. It will be propagating. So if I have million equations, this essentially corrupts all the equations very quickly because every time it's only the 15th decimal place. But if you do it million times, it creeps into 14th, the 13th, the 12th, etc. And eventually you get a solution that is totally nonsense because of round-off errors. So it's something that you need to be aware of. And so what is important in solving with direct methods is to get the scaling right. To scale all your matrices, the elements in A. You don't want one element of A to be million and another element of A to be 10 to the minus 8. That's a poorly scaled matrix. Okay, then you are introducing possibilities for lot more round-off errors. Okay, and that's an important practical knowledge that we need to pick up. That round-off errors can plague. Once they get into the calculation of direct methods, they stay forever, and they continue to propagate and corrupt the solution even more. Any questions? Is that clear? The idea of pivoting, the idea of round-off errors. But if I switch these two terms, these two equations, and solve, everything is fine. Because I don't have this 1 over epsilon term anymore. Okay? The solution simply becomes this. As epsilon goes to 0, it's 1. Okay? And the second one is, second step of the elimination process is 2 minus x2, which is also 1. It gives you the correct result. Now, the Thomas algorithm also I'm going to skip because it is exactly the same as Gaussian elimination. I don't know why they gave it a special name, because the guy developed it before Gaussian elimination. I'm not sure about the history. But it's essentially a diagonal system. So the Thomas algorithm recognizes that in applying the Gaussian elimination, I just need to apply once. I know all these are 0. I'm not going to worry about it. So the number of steps involved in Gaussian elimination becomes extremely simple. And I have indicated what these are. Okay, so there is one loop there, there is one loop there, and one backward loop. There's no really nested loop in this one. But it's exactly the same idea as in Gaussian elimination. But because it occurs so frequently in stage-wise operations, for example, in distillation columns, absorption columns, when you write the mass balance equation, energy balance equation, chemical engineers would understand this. What happens on the tray above and below are connected to what happens in the current tray. So there are 3 elements, 3 links. And if you assemble all the mass balance equations, you get a tridiagonal system. And same thing with finite difference methods that we will see later on. So it's one of the more popular algorithms. Now, Gaussian elimination. I guess maybe I will stop here because I wanted to take this a bit slow to show the important link between Gaussian elimination and LU decomposition. The LU decomposition allows us to capture all the operations that take place in Gaussian elimination once and for all. Once you do that, you give me different sides, right-hand sides, I can improve the efficiency even more than applying Gaussian elimination every time. So we'll come back on Wednesday and continue with this and hopefully wrap linear algebra and then move on to nonlinear algebraic equations. That may take 2-3 lectures because there I want to talk about some of the more recent algorithms for multiple solutions tracking, etc., and demonstrate it using COMSOL. That will be the one assignment that you will do, one last assignment. Okay, so let's stop there. Any questions? So take a look at the project assignments and email me your choice. First come, first serve.